Hi, in this video I'm discussing Unit 5 paper, Edexcel IAL, May, June 2021. Okay, so the first question, MCQ, a detector and counter were placed near a radium source. A student measured the count for 1 minute. He used this value to calculate the count rate in becquerel from the source. Careful, from the source means he wants the actual count rate. You know, when you keep a radioactive source closer to the GM tube window, it will measure the total count or total count rate. If you use a rate meter, it will record the total count rate. Total count rate means the count rate due to the radiation from the source plus the background count rate. So to get the actual value of count rate from the source, you should subtract the background count rate from the total count rate. So here the question is, which of the following would increase the accuracy of the student's value for the count rate? Adding the background count rate, no, anyway, we need to subtract. So answer A is wrong. Increasing the counting time for 10 minutes. Actually, even if you measure longer time, the background count rate will be still there. So you will not get the count rate due to source. Normally, increasing the time will make the accuracy. Yeah, it will increase the accuracy when you measure, say, for example, if you are measuring a count rate for 5 seconds, it might be zero during that time. The reason, radioactive decay is a random process. If you measure for 10 seconds even, sometimes the source might not emit any radiation during that 10 seconds because it's a random process. So normally we can measure for longer time, something like compared to 1 minute, maybe 5 minutes is better. But the question is, the student wants to get the count rate in becquerel from the source. That means he wants to measure the actual count rate. So if you want to measure the actual count rate, even if you measure for a longer time, the background count rate is still there, right? So the answer B is not correct actually, because you must subtract the background count rate. So the correct answer is D. The correct answer is D. Answer C, repeating the count with different detector and calculating in no. Different detector is not necessary. Yeah, normal GM tube is accurate one detector. So answer C also not correct. So to get the actual count rate, you should subtract the background count rate from the total count rate. Correct answer for question number 1 is D. Okay, question number 2. The initial value determined by astronomers for Hubble constant was smaller than the currently accepted value. The Hubble constant value changes. Normally we find the Hubble constant from the graph plotted by Hubble, y-axis, speed of recession, x-axis, distance. Normally there is large uncertainty in the measurement of distance of the galaxy. So because of that, the slope of the graph gives the Hubble constant that will have large uncertainty due to uncertainty in the measurements of the astronomical distances. So the question, it says compared to earlier value of Hubble constant, the recently measured value of Hubble constant has a larger value. Astronomers for Hubble constant was smaller than the currently accepted value. So currently accepted value is larger. There will be changes due to increase in accuracy in the measurements. Which of the following statement is correct? So this question is something like the Hubble constant. Hubble constant itself has no meaning, but 1 over Hubble constant, that is reciprocal of the Hubble constant, gives the age of the universe. Most of you would have done it as a theory in the class. 1 over h is h gives the age of the universe. So we need to think in terms of 1 over h, not directly h. Okay, so the universe is bigger than astronomers. So actually, Hubble constant is nothing related to size of the universe. So answer A is wrong. Answer B, the universe is not as old as astronomers initially thought. Age of the universe is given by 1 over Hubble constant. So recently measured value of h naught is larger, means age of the universe is small. Actual value of age of the universe is lower. So the answer B says universe is not as old as astronomers initially thought. Yes, that is the correct answer for question number 2. We'll check the answer C also. It says the universe is older than, no, older is wrong, because if H naught becomes larger, age is 1 over H naught, so H becomes smaller. So answer B is correct. Answer D, the universe is smaller than, no, H naught is nothing related to size of the, like a dimension, or it does not depend on the volume or size of the universe. So answer B is the correct one for question number 2. Okay, question number 3. When a train travels across a railway bridge, the bridge may be forced into resonant oscillation. You know the meaning of resonance. Maximum amount of energy is transferred from the train to the bridges, maybe resonance, yeah. Which of the following happens only when resonance occurs? Answer A, damping reduces the amplitude of oscillation. Damping happens always. Damping happens always. So that is not a correct answer. B, energy is transferred from the train to the bridge. Energy is always transferred from train to the bridge, but during resonance, maximum amount of energy will be transferred. So answer B also not correct. Resistive forces dissipate energy from the train. That always happens at all frequencies, not only resonance. Every time there will be energy dissipation due to resistive forces. So answer C also wrong. A, B, C, all three answers wrong. Answer D, the amplitude of oscillation usually large. Yes, during resonance, what happens? Large amount of energy will be transferred from the driver. Here, driver is the train. Driven system is the railway track. So large amount of energy will be transferred. So when the large amount of energy is transferred, the oscillation will have larger amplitude. So question number 3, correct answer D. Question number 4. In the sun, nuclear fusion occurs mainly in the core. We know that when it is in the main sequence, sun is in the main sequence, the hydrogen fusion is occurring in the core. Which of the following is a reason for this? Answer A, helium nuclei surrounded the core. Yes, but that is not the reason for fusion is occurring in core. In the core, there will be large amount of hydrogen fusion is occurring. Helium is around the nucleus, a layer of helium. So there will be a little bit of helium fusion also occurring, but because of helium, hydrogen is not getting fused. So answer A is not acceptable. Answer B, most of the sun's hydrogen is in the core. Yes, hydrogen is in the core. That's right. But fusion is happening in the helium also. So the question is, in the sun, nuclear fusion. They didn't say hydrogen fusion. Nuclear fusion occurs mainly in the core because there is large amount of hydrogen in the core. So when the sun leaves the main sequence, you know that the core will be occupied by helium. So when core is occupied by helium, mainly helium fusion will occur in the core, and that will cause explosion, forms a planetary nebula. So answer B, most of the sun's hydrogen is in the core. Yes, it's there, but that is not the reason for hydrogen fusion occurring in the core. To have hydrogen fusion larger, there should be larger temperature. So answer C, the core contains most of the mass of the sun. Yes, but that does not mean larger mass required for hydrogen fusion is not correct. But you can say larger density is required. If they say, we can accept it. Larger density required, to sustain the hydrogen fusion. When the density larger means, hydrogen nuclei are getting very closer to each other, so they can continue the hydrogen fusion. So larger density is required, not larger mass, right? So answer C also not correct. So A, B, C are not correct, or maybe not suitable. Answer D, temperature is greater in the core. Yes, so in the core, temperature is greater. So actually what we say, the temperature of the sun is 5400 degrees Celsius. That is the outer surface, the temperature of the outer layer of the sun. The core temperature will be much more than that one. So temperature is greater. When the temperature is greater, what happens? Hydrogen nuclei will get more kinetic energy, so they will be able to collide with each other and can have fusion because they can overcome the electrostatic repulsive force due to their higher kinetic energy. The higher kinetic energy is provided by the high temperature. So the most suitable answer for question number 4 is D. Okay, question number 5. Okay, the question number 5. The gravitational field strength on the surface of Mercury is Gm. So that is given. So Gm is the gravitational field strength on the surface of the Mercury. And that is given there. Uh, Callisto, a moon of Jupiter, has the same radius as Mercury, but only 1/3 of its density. So you know that this is the Mercury, this is the Callisto, the moon. Both have same radius. If I say this density is rho, the density of the Callisto is 1/3 of it, rho by 3. Okay, so the mass, you know, mass is given by volume into density. So the mass of the this is Mercury. So this is Callisto, some name they are giving it. So its mass is given by volume 4 by 3 pi r cube. Rho is the mass of the Mercury. Mass of this one will be, if I say this is m, the mass of this one m1 will be volume, same thing, 4 by 3 pi r cube, rho by 3. So you can see both have the same radius, means when you compare the mass of these two, the mass of this one is 1/3 of this mass. Is it? Mass of this one will be 1/3 of this mass because volume is the same, both have same radius, but density is 1/3 of this one, means mass of the moon Callisto will be 1/3 of this one. So I can say m1 is equal to m by 3. Okay, so the gravitational field strength of this one is given G equal Gm over r squared. So the gravitational field strength of the Mercury on its surface Gm is equal to G times capital M over r squared. For this one, if I say G is equal to G, instead of mass M1, I can put M by 3 over r squared. So that means this is going to be 1/3 of this gravitational field strength. Okay, so the gravitational field strength on the surface of this moon will be 1/3 of the gravitational field strength on the surface of Mercury. So the correct answer B. Question number 5. Correct answer B. Okay, question number 6. Tau Ceti is one of the closest stars to Sun. The Tau has a surface temperature of 5300 Kelvin and luminosity of 0.55 times the luminosity of the Sun, where L Sun is the luminosity of the Sun. Which of the following is the correct description of this Tau Ceti? Okay, when you consider the HR diagram, you know this is the main sequence. So if I say the sun is somewhere there, now the question is which of the following is the correct description of the Tau Ceti? So its temperature is, for that particular star, the temperature is 5300 Kelvin, almost same as the sun, right? But the luminosity is 0.55 times the luminosity of the sun. So that means it has the same temperature as the sun. If I say this is the sun, this is the position of the sun. So the relative luminosity is 1. So the temperature is almost 5300. So the luminosity is same as, sorry, the temperature is same as the temperature of the sun, but luminosity is much lower. So the question is, it's a main sequence star, they are saying it. We'll see one by one. Red dwarf star. Red dwarf means the stars, those are here. The stars, you know, the 7 classes. In that 7 classes, these are O class stars. So this is the M class stars. They are red. They are the stars called red dwarfs. So if it is a red dwarf, then its luminosity should be much lower and temperature also much lower. You know the temperature is decreasing this direction. So temperature cannot be same as the temperature of the sun. The luminosity should be much lower. But anyway, luminosity can be lower, but temperature cannot be 5300 if it is a red dwarf. Red dwarf is a star on the main sequence. So it cannot be a red dwarf star because if it is red dwarf, then the temperature should be lower. Then second one, it's a red giant star. If it is a red giant star, somewhere here. So red giant star means okay. Then the luminosity should be much more than the luminosity of the sun. So that also not a correct one. Then white dwarf star. If it is a white dwarf, temperature should be much more than 5300 and the luminosity should be lower than the luminosity of the sun. Okay, anyway, luminosity is lower than the luminosity of the sun, but temperature cannot be 5300. It should be much more than this one. So we can see that answer B is not acceptable, not a red dwarf star, not a red giant star, not a white dwarf star. So it could be a main sequence star. Somewhere here, main sequence star means it should be somewhere here in this, this is not a correct exactly straight line. It's a distribution. So it can be this way, somewhere here is like, you can see the chart diagram. So main sequence star, but temperature is almost like temperature of the sun, but somewhere here the luminosity is 0.55 times the luminosity of the sun. So the most suitable answer is A for question number 6. We can eliminate the other answers. So it should be the answer A, right? Okay, question number 7. Helium gas in a closed cylinder is heated until the pressure exerted by the helium is 4 times the original pressure. The volume occupied by the helium stays constant, means you can identify the law here. Volume remains constant. We assume there is no leakage, no change in mass. So that means pressure is increasing when the temperature increases, means pressure law. P1 over T1 equal P2 over T2. So when they increase the temperature, the pressure becomes 4 times the original pressure. So the temperature would have increased 4 times. P proportional to T, P is equal to K times T, or P proportional to T is the pressure law. So compared to initial pressure, if the pressure becomes 4 times, means temperature becomes 4 times, right? The mean square speed of the helium molecules before heating is Vi squared or V1 squared. This is the mean square speed before it is heated. That means when the temperature is T, right? So when the temperature becomes 4 times, how do I know it becomes 4 times? Pressure becomes 4 times. When the temperature becomes 4 times, the question is, the mean square speed of the helium molecules is Vf, the final speed, Vf squared, when the temperature becomes 4 times of the initial temperature. What is the ratio of Vf squared? This is the question. Vf squared, the mean square speed of final temperature over mean square speed of initial temperature. What is that value? That's the question. So you know that the equation, the average kinetic energy of a molecule is directly proportional to absolute temperature. So average kinetic energy of a molecule is given by half mv squared. So average kinetic energy half mv squared is directly proportional or equal to 3 by 2 kT. So initially half m v1 squared equal 3 by 2 k into t. Finally, half m vf squared equal 3 by 2 k times 40. So we need the ratio of this over this, means divide this by this. So I can say this is equation 1, this is equation 2. So 2 over 1 if you find it. Half m will get cancelled. Vf squared over V1 squared will be equal to 3 by 2. 3 by 2 will get cancelled. K will get cancelled. 4t over t will be equal to 4. So the correct answer C. Question number 7. Correct answer C. Okay, question number 8. Two stars P and Q have approximately the same radius. The surface temperature of star P is twice the surface temperature of star Q. So P is higher temperature, twice the temperature of star Q. The star P has luminosity Lp and star Q has luminosity Lq. The ratio of Lp over Lq is approximately. So you know the equation for luminosity, L equal sigma A T to the power 4. Is it? L equals sigma A T to the power 4. They have the same radius, means they'll have the same surface area. This is according to Stefan Boltzmann equation. So same radius means same surface area, but the temperature is twice for the P. So you know the temperature is twice means, so if I say if this is the luminosity of Q, then LP will be sigma A 2T to the power 4. So that means sigma A 2 to the power 4 is 16. So T to the power 4 into 16. The question is, find the value of LP over LQ. So LP over LQ, simple maths. You know, when I divide this by this, sigma A T to the power 4, sigma A T to the power 4 will get cancelled. So the answer is 16. So question number 8, correct answer D. Okay, question number 9. An object oscillates with simple harmonic motion. The period of oscillation 0.55 seconds and the amplitude is 0.25 meter. Which of the following shows a correct calculation for maximum velocity? You know the equation V max equal A omega. So remember that equation, V max equal A omega, and omega is equal to 2 pi over T. We know that. Right. So the simple harmonic motion, the period is given 0.55 and the amplitude is given 0.25. So 0.25 into 2 pi over time period is given as 0.55. So the correct answer is B. Okay, so question number 10. Two stars X and Y behave as black body radiators. The graphs show how the intensity I of the radiation emitted varies with wavelength lambda for two stars. The stars are both viewed from the same distance. So maybe X and Y, the two stars. So they are viewed from the same position, right? The person is here and he is viewing from the same position. So the distance is the same. Okay, so first statement, the star X is brighter and has higher surface temperature than star Y. So brighter, how do I know it's brighter? Means its intensity is larger. So the intensity is larger means it's brighter. Is it? Its intensity. So that they are saying the graph is about, the graph shows how the intensity of the radiation emitted varies with wavelength lambda of the two stars. So that means it is emitting a radiation. So that emitted radiation's intensity, how it is varying when you compare with the wavelength when you receive the radiation. So here you can see that the intensity is higher for a particular wavelength. So according to that, it should be a brighter, the highest intensity. But higher temperature, surface temperature, you can see that smaller the wavelength, the peak wavelength is smaller compared to Y. So according to Wien's law, lambda max T equal 2.898 10 to the power minus 3. That's the Wien's law. According to Wien's law, so the peak wavelength, the wavelength that corresponds to the peak intensity is smaller. That means the temperature of X is higher. Also, its intensity is more, means it should be the brightest. So answer A is correct. Actually, star X is brighter and has higher surface temperature. Brighter because it has the highest temperature compared to Y. The peak wavelength is shorter compared to peak wavelength of Y. So according to Wien's law, the temperature of the X is higher. So the answer for question number 10 is correct. A is the correct answer. If you check the B, the star X is brighter. Okay, that is correct. And has lower surface temperature is wrong. It has higher temperature. I already told that according to Wien's law. Star X is dimmer. No, because its intensity is higher. So brightness something related to intensity. So that is anyway wrong. Answer C. Answer D, star X is dimmer. Okay, that also wrong. So the correct answer for question number 10 is A. Okay, so section B, question number 11, diagram is given. The Boyle's law apparatus is given on the diagram. The school apparatus shown is used to demonstrate gas law. That's the Boyle's law. You know, P1 V1 equal P2 V2. The condition, the temperature should remain constant. Air is trapped in a glass tube of uniform cross-sectional area. A pump forces oil into the base of the glass tube. So all the diagrams are given. This forces air into the smaller volume. The pressure of the trapped air is displayed on the pressure gauge. You know, you would have done this practical. You can see the use of Boyle's law. There are a lot of YouTube videos. You can watch there how it works. So the question is, the pressure of the trapped air increases when the air is forced into the smaller volume. So that means when you are compressing an air at constant temperature, we should assume Boyle's law is applicable only when the temperature is constant, but that is not mentioned in the question. But anyway, they are compressing a given mass of gas. That means the volume is decreasing, pressure is increasing. The question is, explain why the pressure increases. We should explain it by using molecular motion. So actually now we can say Boyle's law apparatus is used to verify the Boyle's law, so the temperature must remain constant. So when you compress the gas, if we maintain the temperature constant, the average kinetic energy of a molecule will remain unchanged even when you compress the gas, because average kinetic energy is given by half m c squared equal 3 by 2 kT. So average kinetic energy has no change even when you compress the gas. So what happened when you compress the gas? All the gas particles are going to be compressed into a smaller volume. Say for example, initially the volume may be this much. The gas molecules are moving randomly in this volume. Now it is compressed, means imagine it is a piston, something like this. So if it is compressed to this volume, means now the whole gas is going to move in smaller volume. That means they have more chance. Their individual kinetic energy has no change. That depends. The average kinetic energy depends same because temperature is not changing. But the kinetic energy, average kinetic energy remains the unchanged. So average speed remains the average mean square speed remains the same, but they are going to move in a smaller volume, means they are going to move in a smaller distance. So what will happen? The number of collisions they are going to produce with one particular wall will increase. So the rate of collision will increase. So rate of collision increases means per second more number of molecules will hit a wall every second. So actually the kinetic energy of each and every gas molecule has no change, so average kinetic energy remains the same. So the force exerted by each and every gas particle during collision remain the same. There is no change. But what happens? The total change in momentum. If you think about change in momentum of one particular gas molecule or any of the individual gas molecules, there is no change in rate of change of momentum because their kinetic energy remains the same. But rate of collision is increasing, so total rate of change of momentum will increase. So total force on the wall of the tube will increase. So total force increases means total force per unit area, that is the pressure will increase. Okay, careful, because no change in temperature, no change in average kinetic energy. That means each and every gas molecule will have the same average kinetic. Same means it won't change even when you compress. The individual kinetic energy will not increase or change. The rate of collision increases. So rate of collision increases means each and every gas molecule during collision will exert the same earlier force when their volume is larger. But number of collisions per second increases will cause total rate of change of momentum to increase. Total force will increase. Total force per unit area will increase. So pressure will increase. That's the answer. So that means here total rate of change of momentum, I said. That means Initially when the volume is larger, maybe for example, just for example, I am taking 1,000 gas particles or air particles might be colliding with the walls of the container. Initially, before you compress the gas, 1,000 air particles might be hitting the walls per second. Each gas particle is exerting, for example, just example, 0.1 Newton. So there will be total force will be 100 Newton exerted every second. Right now, the rate of collision is increasing, but each and every gas particle is going to exert the same earlier force, 100 Newton. So each and every gas particles will exert the same force during collision, but the rate of collision is increasing. So rate of collision is increasing means more particles are going to hit the wall per second, but they are going to each and every particle exert the same earlier force, but rate of collision is higher means per second the total force on the wall will be higher, so pressure will be higher. That's the idea. Okay, question number 11b part. The apparatus is used in a laboratory where the temperature is 293 Kelvin. When the air occupies a volume of 2.43 10 to the power minus 3 meter cube, the reading on the pressure gauge is 1.05 10 to the power 5 Pascal. Calculate the number of molecules of air trapped in the glass tube. So that is simple question. Question number 11 B part. We can use PV equal NKT. You know that equation. So pressure is given 1.05 10 to the power 5. The volume occupied by the gas is 2.43 10 to the power minus 3 meter cube. I need to find the N. K is a Boltzmann constant 1.38 10 to the power minus 23. And temperature is absolute temperature. That means temperature, absolute temperature means it should be in Kelvin scale. So it's given as 293 Kelvin already. So that temperature, if it is given in Celsius, you should add 273 to get the Kelvin scale. So solve it, you will get N. So that will be 6.31 10 to the power 22 molecules. Okay, question number 12. In recent years, astronomers have discovered sources of fast radio bursts, that is FRB, in other galaxies. Studies suggest that these sources may be a type of standard candle. Okay, what is standard candle means? A source, a star or an astronomical object. A star or an astronomical object with known K, no W, known luminosity is called standard candle. So actually, normally we use Cepheid variable as a standard candle, or we can use even type 2 supernova. But in Edexcel syllabus, we never use type 2 supernova as a standard candle. So in your syllabus, we use Cepheid variables as the standard candle. So what is standard candle means? A star or an astronomical object with known luminosity. That's the answer for A part. B part, an FRB, that is fast radio bursts. Source emit intense bursts of radio waves, each burst lasting for a fraction of a second. The closest FRB source is in a massive spiral galaxy, 4.60 10 to the power 24 meter. So maybe that FRB, the burst is coming from some galaxy somewhere here. So we are here. So this distance is given. We are measuring from here. So on Earth, the distance is 4.60 10 to the power 24 meters. Okay, the distance is given. So here is the burst happening, that star, right? The detector of an area 1 into 10 to the power minus 4 meters squared on the surface of Earth. So this is the Earth. We are measuring from here. This is the Earth. We are measuring from here. So we are keeping a detector that has a surface area on the surface of Earth. That surface area is given, that is 1 into 10 to the power minus 4, 1.00 or 1, whatever it is, 1 into 10 to the power minus 4 meters squared is the surface area of the detector we are using on the surface of Earth. In one burst, 9.40 10 to the power minus 23 joules of energy was received in a time of 1.15 milliseconds. So that means we are using this detector, the area is this much to receive the radiation from the burst. So during a time of 1.15 millisecond, we received a total energy of, in this detector, we received a total energy of 9.40 into 10 to the power minus 23 joules we received, right? So we can find the power received by us. We'll see that. Show that the luminosity of the source is, so luminosity of the source, this luminosity is the question, this luminosity is the question. So it looks little bit confusing, too much of data given. We know that if we have a source here, and normally we take all the most of the astronomical objects, like whether supernova or whether star, that obeys like a black body radiator. So we can use the equation intensity or radiation flux, either one of the symbol we can use. I or F is equal to L over 4 pi d square. All of you know that. So in this question, the question is L is the question. So L is the luminosity of the source. We need to find it. D, we know that distance of the Earth from the that particular galaxy, we know the distance also given. The intensity is not given. So all these data are given to find the intensity of that radiation on the surface of Earth. So we know the energy we receive during this time. We know the energy. So I can write power of the radiation received on the surface of Earth. I can write, so question number 12, A part, I can say power of the radiation received on the surface of Earth, on Earth, equal energy divided by time. So 9.40 10 to the power minus 24 divided by the time. So 1.15 millisecond 10 to the power minus 3 seconds. Convert millisecond to seconds. So that will be 8.17 10 to the power minus 20 watts. That is the power of the radiation we are receiving on the surface of Earth. That power of the radiation is emitted from the burst, right? So intensity of the radiation received on the surface of Earth, you know the equation, intensity equal to power per unit area. So this power is received by this area, 1 into 10 to the power minus 4 meters squared. That detector is receiving this power. So what is the intensity received by the detector, or what is the intensity of the radiation received on the surface of Earth, because this is kept on the surface of Earth. So I can say intensity of the radiation received on Earth, I can say I equal P over A. I know the power received, that is 8.17 10 to the power minus 20 divided by surface area of the detector, 1 into 1.00 10 to the power minus 4. So the intensity what we received is 8.16 10 to the power minus 16 watts per meter square. Okay, so now I know the every data, all the data I know that. I know the intensity we received. I know the distance of that star from where the radiation is emitted. I need to find the luminosity of the star. So now I can use I is equal to L over 4 pi d squared. So intensity I know 8.16 10 to the power minus 16 equal. Luminosity is the question. 4 pi d squared. D we know that 4.60 10 to the power 24 holding squared. From this, find the luminosity. L will be 2.17 10 to the power 35 watts. That's the luminosity of the burst, the star where it emits the burst. It's 12D part, not 8 part. This is 12D part. Okay, so question number 12, B part, first part we answered. We found the luminosity of that particular star where the burst happens. We found the luminosity as 2.17 10 to the power 35 watts. Now, question number 12, B part, second part. When FRB sources were first discovered, some observers suggested that the burst might be alien communication. Suggests why this is unlikely, right? Little bit of analytical type of question. Only just 2 marks. Luminosity of the sun is given 3.8 10 to the power 26 watts. Okay, so here we can say like this. Now, actually, compared to the luminosity of the sun, which is 3.8 10 to the power 26, that's the luminosity of the sun is 3.8 10 to the power 26 watts. The burst gives luminosity of 2.17. That burst we already calculated it. 2.17 10 to the power 35. So this burst is almost 5 into 10 to the power 8 times of luminosity of the sun. So that you are, when you do that, you will get 1 mark most probably for this calculation. Compare it, because there's nothing relationship between the luminosity of the sun and luminosity of the burst, right? The origin where the burst happens, it's giving a radiation with a particular luminosity. So only thing you have to compare it, how many times it's more. So that burst is almost 5 into 10 to the power 8 times of the luminosity of the sun. That you will get 1 mark, total 2 marks. So what is the next mark? So there it depends. You can say practically it is not possible to create such larger luminosity of radiation. Yeah, we can say that, but we don't know. The aliens are very intelligent than us. They might be able to do that. We don't know that. But according to our knowledge on Earth, we can't create a radio like a source that can emit a radiation, electromagnetic radiation, that is this times the luminosity of the sun. Not possible. You can say that, right? They maybe they can create. We don't know, but according to our knowledge, according to the scientific facilities we have on Earth, we can't create. So we assume they also can't create. So the second mark, you should say, since the luminosity is very large, it's difficult to create such high radiation artificially. Okay, question number 13. Interesting question. So they are saying in the book Charlie and Chocolate Factory, a palace is made entirely. Question number 13 I am discussing now. A palace is made entirely from chocolate. Soon after it was made, the palace melted due to energy transferred from the sun. You know, sun radiates thermal energy, so chocolate can melt, right? So the palace, which is made of chocolate, melted due to the radiation from the sun. Okay, the total volume of the chocolate used for the palace was 1250 meter cube. The initial temperature of the chocolate palace was 28.5 degrees Celsius. Chocolate melts at temperature of 36 degrees Celsius. So that's a melting point of the chocolate. So if the initial temperature of the chocolate when the palace was made initially 28.5 degrees Celsius. If it wants to melt, the temperature of the chocolate must be increased to 36 degrees Celsius, otherwise it will not melt, right? So the book states that the palace melted completely in less than a day. So, less than a day means we can take it as 12 hours per day or even maximum 24 hours. But sun, the radiation from the sun can be received maximum 12 hours. But some countries might get more than 12 hours. We don't know. We'll see, right? Deduce whether this statement could be correct. Okay, so here in this question, they are not asking you to do any specific calculation, find this one, find this one, they are not saying it. But some data given additionally, rate of energy transfer to the palace given from the sun, that is power radiated from the sun to the chocolate palace is given 7.5 10 to the power 5 watts. Density of chocolate given, specific latent heat of means latent heat of fusion of chocolate is given 4.5 10 to the power 4. Specific heat capacity of the chocolate is given. So the question is, deduce whether this statement is correct. So the statement is, the book states that the palace melted completely in less than a day. So when students read this question, mostly smart students will get the idea, what should I do? What work or what calculation should I do, right? So the aim of this question, they are not asking you to specifically find this value or this value, whether the statement is correct. Identify the statement. Statement says it completely melted less than a day. So we will find out how long it will take to melt a volume of chocolate of 1250 meter cube completely. How long will it take? If the radiation given is 7.5 into 10 to the power 5, if the radiation given is 7.5 into 10 to the power 5, how long will it take to completely melt the chocolate? So we will find the time. Then compare the time taken to completely melt with 1 day, that is 24 hours. We'll compare it with that 24 hours and we'll check whether the statement is right or wrong, right? So we are going to say, now we know that this is the palace initially at a temperature of 28.5 degrees Celsius. So melting point is given at 36, means if you want to melt the palace completely, you should bring the temperature to 36 degrees Celsius from 28.5. The temperature is received from the sun at a rate of 7.5 10 to the power 5 watts. So first we will see how long will it take to bring the temperature from 28.5 to 36 degrees Celsius, right? So we'll find that one. So I can say the time taken to increase the temperature from 28 degrees Celsius, 28.5 degrees Celsius to 36 degrees Celsius is T1. I'm taking it, the time taken as T1. So during this time T1, how much of energy given to the chocolate? That is equal to power into time. Power is given 7.5 into 10 to the power 5 T1, energy equal power into time. So that is the total energy given when the temperature increase from 28.5 to 36 degrees Celsius. So we will find out that time. So we know that E is equal to mc delta T or delta theta, some books they use. So energy is 7.5 10 to the power 5 T1 equal mass of the chocolate. We know that density equal mass over volume. So I can say mass is equal to volume into density or density into volume. So I can substitute in some mass. Density is given, volume is given. So density is given 1325 kilogram per meter cube into volume is given as 1250. So that is the mass. Specific heat capacity of the chocolate also given, that is 1.30 10 to the power 3 joule per kilogram per Kelvin. The temperature increases 36 minus 28.5. So everything no. So we can find the time T1. So the T1 will be 21,531.3 seconds. So we can find it in minutes or hours, but I leave it as seconds. That's the time taken to increase the temperature from 28.5 to 36 degrees Celsius. Now it has reached the melting point. Now the chocolate is going to melt. We know the equation for melting. So the energy required to melt the, so I can say the time taken to completely melt the palace or chocolate palace is T2, right? So we know the equation. So the energy given during that time. So I can say this E1. So the E1 I found it. So E2, the energy given during melting is equal to E2 is equal to power, that is 7.5 10 to the power 5 into T2. That's the energy given during melting of the chocolate. Completely it's melting. And we know the equation E is equal to delta M times latent heat of fusion. We know the equation. So E I know that 7.5 into 10 to the power 5 T2 is equal to, so the chocolate is completely melted. So the same mass as here, 1325 times 1250, that's a mass into density. That's the total mass of the chocolate palace. That into latent heat of fusion is given. Specific latent heat of fusion is 4.5 into 10 to the power 4. From this, find the time T2, how long it takes to completely melt the chocolate. That will be 99,375. So total time taken at the two times. So that is 21,531.3 plus 99375. So that will be 120,906 seconds. That is the total time taken. I'll put it as capital T. So again, I'm writing here. So capital T, I'll write it here separately. No space on the board. So capital T is equal to the total time taken. Capital T will be equal to 120,906 seconds. You can convert to hours, divide by 60 into 60. So 120,906 divided by 60 into 60 hours. So that will be, you will get 33.6 hours. That is much greater than 1 day, that is 24 hours. So it's a wrong statement, or you can say it's a wrong statement. Okay, question number 14. A student set up a simple pendulum. The student used a velocity sensor connected to a data logger to record the velocity of the pendulum bob. The graph shows how the velocity of the bob varies with time. So the velocity time graph is given. on the question paper. Add a line to graph to show how the displacement of the bob varies. So to get the displacement from displacement time graph from velocity time graph, remember this way. Different teachers teach different ways. Some teachers, they say shift the y-axis of the graph. I usually say shift the y-axis of the graph. Some teachers, they say shift the graph itself. But normally I teach like this. To get from the displacement time graph to get the velocity time graph, shift the y-axis of the graph towards right. You know, easy to remember. Displacement time, velocity time. I am showing the arrow from displacement time to velocity time, showing to the right, right? So shift the y-axis. Shift the y-axis towards right through t by 4. So if I shift this y-axis towards right by t by 4, that means if I put a t by 4, if I put this one here, this is if it is a displacement time, I'll change it. If it is a displacement time graph, if it is a displacement time graph, and if I shift it to the right by t by 4, I will get a velocity time graph. Same way, from velocity time graph to get acceleration time graph, again shift the y-axis of the velocity time graph towards right through t by 4. Say for example, if the displacement time graph is like this, to get the velocity time graph, shift the y-axis towards right. That means if I put a y-axis here, the shape is starting from here. That will be the velocity time graph. So the velocity time graph will be like this. So to get the velocity time graph, shift the y-axis towards right through t by 4. So the graph will start like this. So the velocity time graph will be like this. To get the acceleration time graph from the velocity time graph, again shift the y-axis of the velocity time graph towards right through t by 4. So if you shift this one through t by 4, the graph will start like this. If I shift it to the t by 4 towards right, graph will start like this. So the acceleration time graph will be like this. Now you can see the acceleration time graph and the displacement time graph are mirror images. If I keep a mirror here, it's shifted here. Actually, inverted graphs. So to get the acceleration time graph from displacement time graph, invert the graph, you will get the acceleration time graph from the displacement time graph. So opposite way, to get the velocity time graph from acceleration time graph, towards left you are moving. So shift the y-axis towards left through t by 4. To get the displacement time graph from velocity time graph, again shift the y-axis towards left through t by 4. So here the given question, this is the velocity time graph, and they ask you to sketch the displacement time graph. So velocity time graph is given. I need to get the displacement time graph, means I should shift the y-axis towards left. If I shift it towards left, so the graph will be continue like this. The graph will be continued like this. So the displacement time graph will be starting from the origin. So the displacement time graph will be like this. If I put it's on a grid, we can draw easily. On the board, little bit difficult. So if I shift it to the left through t by 4, the graph will start like this. So the velocity time graph will be like this. Will be like this. The green color indicates that this is the velocity time graph. Okay, question number 14, A part. Second part, determine the length of the symbol pendulum. So from the graph, from the given graph, you can find the period, time taken for one full oscillation, that is 2 seconds. So use the equation T equal 2 pi square root of L over G. So 2 seconds equal 2 pi square root of L over 9.81. Solve it. You will get the length, that will be 0.99 meter or 1 meter. So B part, question number 14. Uh, in some experiments, it is an advantage to use data logger rather than other measuring instruments. Describe when the use of data logger is an advantage. So you can say the two advantages because 2 marks only given. One, you can say the data logger can be used for very short time measurements. Say for example, in case not only this one, anywhere when you are taking some data collection, if you need to measure the quantity during something like 0.5 seconds, we can't measure it, or 0.5 seconds interval, we won't be able to measure it manually. So there we can use a data logger. So 1 mark you will get if you say when data is collected over short time period, data logger are suitable. Then you can say for multiple data collection, more than one data if you want to collect, there also data loggers are suitable. Okay, question number 15. A graph of relative intensity against wavelength for a star is given. So the graph is given something like this. Determine the surface temperature of the star. So from the graph, find the wavelength that correspond to the highest intensity. So that you will get is 0.38. This value will be 0.38 micrometer. So the wavelength is given in micrometer. Now use the Wien's law. Lambda max T times T equal 2.898 10 to the power minus 3. Substitute the value. This is lambda max is 0.38 10 to the power minus 6 into T, the temperature, is equal to 2.898 10 to the power minus 3. Find the temperature T. You will get 7626 Kelvin. That is the question 15, A part. Okay, so B part, question number 15, B part. So this diagram is given for emission lines. So radiation from the star is analyzed. The radiation from the star has spectral lines at different wavelengths from the same spectral lines produced by the source in the laboratory also given. So this is for the spectral line for the radiation from the star. This is the spectral line for the same spectral line in the laboratory. Explain what can be concluded about the star from these results. Your answer should include a calculation. So there you can see the values are given, something like here 500. So like that they are given, that is the wavelength in nanometer. X-axis is wavelength in nanometer. There are some dots given. Each interval of the dots is 20 nanometer, 20 nanometer. So you can see between 500 to 600 there is a 5 dots. So each small division of the dots is 20 nanometer. So there, I need to use Doppler effect, delta lambda or lambda equal V over C I can use. So this is the spectrum from the star. This is the same spectrum in the laboratory. So I can use one of the spectral lines. So this is from the star means this is the lab. So this is larger than this. So if I say this is the spectral line in the laboratory, the corresponding spectral line for the star is this one. So this is the delta lambda. The difference in the wavelength, this is the delta lambda. So you can read it from the graph. So you can, if I'm using these two spectral lines, this is actually 600 here, the dot is here. So this is more than 620 nanometer, but not equal to 640 or 630, because 630 is somewhere here. So this is not, this spectral line is not exactly mid of the two dots. It's more closer to this dot. So I can take something like 623, 24, 25 up to 630. I can take any value. So I took it as 622 nanometer. Even if you take 623, no problem. So there is no specific value, but we can see that this is 600. So this is more than 620. This dot is here, 620. The line is slightly on the right side of the 620, but not even at the center of these two dots. If it is at the center, then I can say that will be 630, but that is not 630, less than 630. So we can take it as something 625, 622, 622, anything we can take, they will accept it. So that wavelength I am taking it as 622 nanometer. So for the same spectral line in the star, that I take it as 655. So that also you can see on the right side of two dots. So 600. So this is at 600. So you can see the mark 600 is here. The next dot 620, next dot 640, but this is more closer to 660, but not equal to 660, more closer to 660. So I can take it as something like 655, 656, anything. I'll take it as 655 nanometer. Okay, so I need to use the Doppler effect equation, delta lambda over lambda equal V over C. So this wavelength which is obtained in the laboratory has larger wavelength, 655. So that means, you know, wavelength is increasing, means it's receding. The star is moving away from us. We can find the speed, at what speed is it moving away from us. So delta lambda will be 655 minus 622 over actual wavelength 622. I don't need to convert nanometer to meter, because numerator denominator 10 to the power minus 9 will get cancelled. Equal to V over C 3 into 10 to the power 8. I can find the speed, that is equal to 1.6 10 to the power minus, sorry, 1.6 10 to the power 7 meter per second. So different students will get slightly different answers depending on the value you are taking for this spectral lines. It's okay. So the answer will be, the speed is this much. So you can say, after doing this calculation, you can say the star is receding or moving away from us at a speed of this much. That's the only final answer we can give in this question. Okay, question number 16. In 2015, the company SpaceX stated its plan to launch about 4,000 Starlink satellites into a low Earth orbit. These satellites would provide a low-cost internet service to people. So the height actually, so the height of the satellite is given 550 kilometer above the Earth's surface. So question number 16. This is the Earth. So the height of the satellite is from the surface of the Earth, that is 550 kilometers. And the mass of the Earth is given, 6 into 10 to the power 24 kilogram. And the radius of the Earth also given, that is 6.4 10 to the power 6 meter. The question is, calculate the orbital time. So simple, we know that the satellite is moving on a circular path. It needs a centripetal force. That centripetal force will be the gravitational pull by the Earth. So I can say the centripetal force F equal, provided by the gravitational pull, that is G, mass of the Earth, times mass of the satellite, over r square. R is the radius of the orbit, so that's measured from the center of the Earth, is equal to mr omega squared, or I can use mv squared over r, but I am using mr omega squared because I need to find the omega. I need to find the time period. Okay, so here the mass of the satellite will get cancelled. So R cube, then you cross multiply. So GME will be equal to R cube into omega. We know that omega equal 2 pi over T. So 2 pi over T all things square. So make the T subject. T squared is equal to 4 pi squared. When I square it, 4 pi squared over GME into R cube. Okay, I need to find the time period. So I got the expression for that. So that is 4 pi squared over G is 6.67 10 to the power minus 11. Mass of the Earth is given 6 into 10 to the power 24 into R cube. R is the radius of the orbit. I need to add the height plus radius of the Earth, and also I need to convert to kilometer to meter. So that is 6.4 10 to the power 3 uh, sorry, 6.4 10 to the power 6 meters. So 6.4 10 to the power 6 meters, that is given, plus 550 kilometer, convert to meter, 550 into 10 to the power 3 meters, all the cube. So R cube, all the cube. Okay, so that is T squared. Find the time period, solve it and take square root of it. You will get 5,755 seconds. If you want, you can give it in minutes or in terms of hours. Okay, question number 16b. But explain why satellites in low Earth orbits have a smaller orbital time than the satellites in higher Earth orbit. So, there first you should say, question number 16b part. First, you should get that equation. Already we derived it. T squared equal 4 pi squared over gm into r cube. Now, we can say when G and M are constant. That means for a given planet around which satellites are orbiting at different heights, so the mass of the planet is constant. Only the height of the satellites we are varying. Mass of the planet is constant, around which satellites are going to be in orbit at different heights, if I consider. So G, anyway, we know constant. M is constant, mass of the planet. So when G and M are constants, I can say T squared proportional to R cube. So I can say T proportional to square root of R cube. So lower orbit means smaller R. So low orbit means the radius of the orbit will be smaller. Therefore, T will be, since T proportional to R cube, T proportional to square root of R cube, for lower orbit, T will be lower or smaller. That's the answer for question number 16, B part. Okay, question number 16, part C. The satellites were launched into orbit using rockets able to make multiple space flights. Calculate the minimum kinetic energy required to raise the satellite to its lower orbit height. Mass of the satellite given. So we found the lower orbit height. Already we know that. We know that height of it. Already we used that in the previous part. So we need to find the minimum energy required. So there you can say loss in kinetic energy equal gain in gravitational potential energy. So when the satellite is orbit from the surface of the Earth, this is the Earth. So it's all launched from here. So that means this is the center of the Earth. So this is the radius of the Earth, RE. From this point to lower height, the lower orbit somewhere here. So this position is launched. So the height, we know the total distance, already we used it in the previous question. This is 550 kilometer above the surface of Earth. Okay, so when it moves from the surface of Earth to this position, what is the gain in gravitational potential energy? You know, gravitational potential is given by V equal minus Gm over R. So that means the gravitational potential created by the Earth around it at a particular distance r from the center of the Earth is given by, outside the Earth at a distance r from the center of the Earth, is given by minus gm over r. If I keep an object of mass m at that point, the gravitational potential energy of that mass is given by v times the mass of the object, that is minus g m over r times m. Okay, so when the satellite moves from surface of the Earth to uh, the lower orbit position, R is changing, so there will be gain in gravitational potential energy. You know, in terms of gravitational potential energy, minus 6 joules, minus 12 joules if you consider, minus 12 joules is smaller than minus 6 joules in terms of negative sign. So you can see when the R increases, the numerical value will decrease. So in terms of negative sign, the value of the energy will increase. So I can say gain in gravitational potential energy equal the gravitational potential energy at this position at lower Earth, lower orbit, that is minus gm m over r2 minus gm m over re, because r1 I can put, but initially it was on the surface of the Earth. From the surface of the Earth you are launching it, so that will become minus 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 plus. So gm m over re minus gmm over r2. I can take gmm commonly, gmm within bracket 1 over re minus 1 over r2. That is the gain in gravitational potential. That will be equal to loss in kinetic energy. That's the question, no? What is the minimum kinetic energy required? Initially, when you are throwing it, you are giving a particular kinetic energy. What is the minimum kinetic energy? Means the final kinetic energy becomes 0 by losing all its kinetic energy, minimum energy, right? So anyway, I'll find the gain in gravitational potential energy. So this is 6.67 10 to the power minus 11 into mass of the Earth. We know that 6 into 10 to the power 24 into mass of the satellite given 227 times, we have to substitute the values inside the bracket. So that will be 1 over radius of the Earth, that is 6.4 10 to the power 6 minus 1 over, the R2 is the radius, that is the radius of the lower orbit, that will be radius of the Earth plus height. So that is 6.4 10 to the power 6 plus 550 into 10 to the power 3. Okay, solve it. You'll get the answer. That will be 1.12 10 to the power 9 joules. So when the rocket moves from the surface of Earth to the lower orbit, it will gain this amount of gravitational potential energy. So if you are launching it, you would give initially, to push it up, you need to give initially a kinetic energy. So the required minimum kinetic energy, also this one, I can say required minimum kinetic energy equal to gaining gravitational potential energy. So that will be 1.12 10 to the power 9 joules. Okay, question number 17. A student suspended a spring from a rigid support. The stretch spring, she stretched the spring by hanging a mass from the free end of the spring. So there's a diagram given on a vertical plane. Spring is hanging and a mass is attached to the spring. Explain why the mass moves with simple harmonic motion. So it's a very common question. 1 mark. You should say, first point you should say, the resultant force acting on the mass is always towards the equilibrium position. Therefore, the acceleration is always towards the equilibrium position. Again, I'm telling, first point, the resultant force acting on the mass is always towards the equilibrium position. Therefore, the acceleration is always towards the equilibrium position. That's a 1 mark. Second mark, you can say the acceleration is always directly proportional to the displacement of the object or displacement of the attached mass. So these are the two reasons to say the oscillation is simple harmonic. Okay, so the B part, question number 17, when the mass on the end of the spring was 0.20 kilogram, the extension of the spring was 7.50 centimeter when the mass was at equilibrium position. So if the mass is at equilibrium position, you know the two forces acting on the mass are the vertically upward, the force due to the extension of the spring according to Hooke's law, F equal K times delta X, and the other one is the weight. If it is at equilibrium position, these two forces will balance each other. Show that the stiffness K of the spring is 26 Newton per meter. So the question number 17, B part, I can say these two forces are balanced at the equilibrium position. So K times delta X equal mg. So mass is given 0.2 kilograms. So extension is given. So attached, so 0. So K we need to find times delta X is given, that is 7.50. 10 to the power minus 2 equal mass 0.2 times 9.81. Find the K. You will get 26.16 Newton per meter, approximately 26 Newton per meter. Okay, question number 17, part B, second part. A graph is given. The student used a stopwatch to determine the frequency of oscillation f of the mass m. She replaced this procedure for 4 more values of mass and obtained the following graph. So there's a graph given for by considering the oscillation of the spring. So you know y-axis frequency squared, x-axis per kilogram, that is m to the power minus 1. So they are plotting a graph of frequency against 1 over mass. The question is, student used to graph to determine a value of k. Deduce whether the graph gives a value of k consistent with the value of spring. So earlier we found the spring constant already by keeping the spring at rest at the equilibrium position. We measured the static extension and we balanced the weight to air F equal K delta X, and we found the K. Now here the student let the spring to oscillate and he is measuring the frequency of oscillation, and he is plotting a graph of y-axis frequency squared, x-axis 1 over mass attached, and he is using the graph to find the K. The question is, find the value of K, and we need to decide, actually same spring we should get the same K, but we should give a conclusion whether this K is acceptable or is consistent with the value of we found in the previous part. We'll simply find the percentage difference. So we'll find the K here. So to find the K, we know that question number 17, B part, second part. We know the equation T equal 2 pi square root of m over K given in the data sheet. So T means 1 over frequency square on both sides. So 4 pi squared into m over k equal 1 over f squared. Make the f squared subject because he is plotting a graph f squared on the y-axis. So I'm making the f squared subject. F squared is equal to k over 4 pi squared into 1 over m. So this is in the form of, this is on the y-axis. This is going to be the gradient. So careful, this is gradient, this is 1 over m as an x-axis. You will get a straight line through the origin. Okay, so from the graph, find the gradient. Find the gradient. So gradient equal that is m. Careful, this m gradient, this is attached mass. Both are m. Okay, gradient m is equal to, from the graph find it, take two clear points from the graph. So that is equal to k over 4 pi square equal to, use the graph now. So m means k over 4 pi square, is it? Use the 2 points, clear points. I took 2.6 minus 0.2 over 4.0 minus 0.5. I found a value of k, second value of k, 27.1 Newton per meter. So first value I got 26.16 or 26.2 I can say. Okay, so is it consistent? This value, now I got it. Earlier I got a value k is equal to 26.16 or 26.2 Newton per meter. They are different, not exactly same. So can we accept these answers as consistent values of k? Okay, so that is unit 3. We will find the percentage difference. So percentage difference equal difference between them. So 27.1 minus 26.2 divided by, if we know one of the answer is the actual value, we have to divide by that. But here we don't know which is the actual one. We have two different measurements or measured quantities for the same quantity. Two different measured values for the same quantity. So we should find the average of them. Yeah, 27.1 plus 26.2 divided by 2. That's average into 100%. So find the percentage difference. You will get that is almost 4.1 percentage. That is less than 5%. So I can say since the percentage difference (5%), we can accept both answers or it's consistent. Okay, question 18. Many countries use nuclear power stations to provide electrical power. Question 18. Energy is released when nuclear undergoes fission in the core of the reactor. State what is meant by nuclear fission so that everyone knows that all the books have that answer. Splitting massive unstable nucleus into more stable, lighter nuclei. Again, I'm telling, splitting massive unstable nucleus into more stable, lighter nuclei is called nuclear fission reaction. Okay, that is the A part, question number 18. B part, first part. Sketch a graph to show how the binding energy per nucleon varies with nucleon number for a wide range of isotope. I don't need to draw. You can find it in your teacher would have given. All the books have the graph, so I'm not drawing it. Okay, so question number B. Second mark the position of the ion. So on that graph, the peak value, the highest point is the ion that is the most stable nucleus. All of you know that. Okay. Now C part, question number 18. Complete the nuclear equation below. So we need to complete. Okay, so we need to complete this. Okay, so you know mass number should be conserved, atomic number should be conserved. So neutron 1 0, all of you must remember 1 0 I can put first. So now 2 into 0 is 0, so 38, this is 92. So here this must be 54. So here 141 plus 2, so this must be 93. Okay. Okay, so next part, the part D. Calculate in mega electron volt the binding energy per nucleon for a nucleus of uranium-236. You know binding energy, what is it? Minimum amount of energy required to break a nucleus into individual free nucleons is called binding energy. So binding energy we calculate by using mass deficit. It's a theory. The total mass of the nucleus is always smaller than some addition of the masses of the protons and neutrons. So why that happens? Certain amount of total mass of the protons and neutrons are used to is converted to energy according to E equal mc squared. It's converted to energy to bind the nucleons together. So that's the reason mass of a nucleus is smaller than total mass of the protons and neutrons of the nucleus. So we find the binding energy by using mass energy equation equal mc squared. First, we find the mass deficit of the nucleus. How do we find the mass deficit of the nucleus? Find the total mass of the protons. How do you find the total mass of the protons? Number of protons into mass of a proton. Total mass of the neutron, number of neutrons into mass of the neutron. Add both, that will give the total mass of the nucleons. From that, subtract the mass of the nucleus. You will get the mass deficit. That mass deficit is equal to it has equal energy, so that mass deficit into, it must be in kilogram, that mass deficit into c squared gives the binding energy in joule. When you divide the binding energy by total number of nucleons or nucleon number, you will get the binding energy per nucleon. So here mass of a proton given, mass of a neutron given, mass of the uranium nucleus given, all are given in giga electron per volt per c squared. Okay, so we'll find the mass deficit delta M, that is equal to total mass of the protons. So mass of a proton is 0.93827. So 0.93827 into total number of protons. So that is uranium. That's the nucleus. Uranium 236, 92. So this is the number of protons. Number of neutrons is 236 minus 92, that is 144, is the total number of neutrons, right? So total mass of the protons, that is mass of a proton into number of protons, plus mass of a neutron is given, that is 0.93956 into number of neutrons, that is 236 minus 92, that is 144. Okay, I found the total mass of the protons and neutrons. From this, if I subtract the mass of a nucleon, that is 219.8750, I will get the mass deficit in giga electron volt per c square. So that will be 1.742 giga electron volt per c square. Okay, so binding energy equal mass deficit into c square. So mass deficit given in giga electron volt per c square. So into c square. C square will get cancelled. I'll get it in giga electron volt. So that will be 1.742 giga electron volt. The question is binding energy per nucleon. I should divide by nucleon number of the uranium, that is 236 is the nucleon number. So binding energy per nucleon binding energy 1.742 giga electron volt. I can keep 10 to the power 9 electron volt over 250/36. So solve it, you will get the answer, that is 7.38 10 to the power 6 electron volt. I can say 7.38 mega electron volt. So binding energy per nucleon is the minimum energy required to remove one of the nucleon completely from the nucleus. Okay, question number 18 C part. Ultraviolet radiation is produced when alpha particles interact with air. So whenever alpha particles hit air, UV radiation will be produced. This can be used to detect alpha particles when a nuclear reactor is decommissioned. Okay, so explain how UV is produced by alpha particles in the air and why detecting UV has advantages compared with detecting alpha particles directly. So you know what are the difficulties in detecting alpha particle means it can travel only 5 centimeter in air. So you need to keep the detector something like Geiger-Müller counter or whatever the detector within 5 centimeter of its range, otherwise it can't travel. So you can't detect the alpha particle unless you keep the detector from the origin where the alpha particle emitted, from that origin the point of emission within 5 centimeter, otherwise you won't be able to detect the alpha particle. But if it is emitting UV radiation due to interact with air, that UV radiation has infinite, theoretically infinite range. Radiations have a much larger range in air, so that can be detected. So the question is, explain how UV is produced. We need to explain when the alpha particle interacts with air, how UV is produced. One question. Then we should have produced by alpha particles in the air and why detecting UV has advantages compared to detecting the alpha particles. So that I already told, the range of alpha particles lower. I need to explain how UV is produced. When alpha particles hit the electrons, one of the electrons of the atoms of an air particle, the electron will absorb the kinetic energy of the alpha particle and excite it to higher energy level. When the electron jump back or de-excite or return to the ground state, it will emit the energy of the difference of the energy levels as one photon, and according to delta E equal HF. So if the difference of the energy level gives a frequency which is in the UV spectrum, that will be emitted as UV radiation. Okay, question number 19, the last question of this paper. A pacemaker is a device used to regulate a person's heart rate. Some of the first electronic pacemakers used an isotope of plutonium as the power source. Plutonium decays by alpha emissions. How the energy released show that the energy released when a nucleus of Pu-238 decays into a nucleus of uranium is about 5.6 mega electron volt. So here also we need to find mass deficit. During alpha decay, beta decay, there will be mass deficit. That means the total mass of the nucleus of the parent, that is parent nucleus mass, will be always greater than total mass of the daughter nucleus and the particle release. So there will be mass deficit. So that means difference between the parent nucleus and the total mass of the daughter nucleus and the product is called mass deficit. That mass deficit has equal energy, that will be the energy released. Okay, so here question number 19, A part. So plutonium 238 is decaying into uranium and alpha 42, there will be energy release. That energy is the total kinetic energy, the kinetic energy of the alpha particle and the kinetic energy due to recoil motion of the uranium nucleus also. Okay, we need to find it. So the mass deficit delta M is equal to mass of the plutonium nucleus minus mass of the uranium nucleus plus mass of the alpha. Okay, find the mass of the plutonium is given in unified atomic mass unit 237 0.999 minus mass of the uranium nucleus 233.991578 plus mass of the alpha particle 4.001506. Use all the decimal points when you are calculating the mass deficit. Don't make any approximations because the tiny differences, if you approximate, someday you might get negative mass deficit. So careful, don't approximate it. Use all the masses given all the decimal points. Okay, so you'll get here. Now I can approximate. After doing this, now next step I can approximate 6.01 10 to the power minus 3 unified atomic mass unit. We know 1 U is equal to 1.66 10 to the power minus 27 kilogram. That's given in the data sheet. So convert to kilogram. So that will be 9.97 10 to the power minus 30 kilogram. So energy release is given by delta M times C squared. So 9.97 10 to the power minus 30 into 3 into 10 to the power 8 all things squared. So that will be they asked me to find the energy release in mega electron volt, so I'll get it in joules if I solve this. To convert it into mega electron volt, 9.97 10 to the power minus 30 into 3 into 10 to the power 8 all in square. That will be in joules to convert to mega electron volt. First, to divide by 1.6 10 to the power minus 19, I'll get it in electron volt. To convert to mega electron volt, again divide by 10 to the power 6. So the final answer will be 5.61 mega electron volt. That's the total kinetic energy of alpha particle and the kinetic energy of recoiling uranium nucleus. Okay, B part, question number 19. In one pacemaker, the activity of the plutonium source was measured to be 6.75 10 to the power 10 BQ in 2020. That is the year, 2020 is the year. Calculate the power of the source in watts when it was fitted 40 years ago. Half-life is given in years. Energy of an alpha particle also given 5.6 mega electron volt. We found it in the previous part. The energy release 5.6 mega electron volt. I told that is the total energy of the alpha particle and the recoiling uranium nucleus. But we can show that the most of the energy of the energy release will be taken by the alpha particle because compared to uranium nucleus, mass of the alpha particle is much lower. Momentum is conserved. The same question appeared, I discussed already in October 2021, similar question. So watch that one. So there we can show that most of the energy release will be taken by the alpha particle because its mass is much lower compared to mass of the uranium nucleus. Okay, something else I told now. Okay, we'll come back to the question, B part. So energy release is given as 5.6. What I calculated in the previous part is given as the energy of the alpha particle. Okay, so here I need to find the power of the source. So how to find the power of the source? Remember the equation. Power of the source is given by activity times energy released per decay. Careful. Activity times or activity into energy released per decay gives the power of the radioactive element. So energy released per decay here is 5.6 mega electron volt. That will be taken as the energy of the alpha particle. Okay, so only thing I need to find the activity. Activity 40 years back. So I know the activity currently, that is 6.75 10 to the power 10. So I need to use A equal A naught e to the power minus lambda t. I need to find the lambda. So that is half-life is given. From that I can find it. So plan it like this. So question number 19 B part. Half-life is equal to ln2 over lambda. So lambda equal ln2 over half-life. ln2 over half-life is given as 87.7 years. So I'll get the lambda in terms of per year. So that will be 7.90 10 to the power minus 3 per year. Okay, so now I can use the equation A equal A naught e to the power minus lambda. I know the activity now. I need to find 40 years back. Lambda is given in per year, so I can find the t. I can keep the time in years. So always in this equation, the unit of time and the unit of lambda should be the similar. For example, if the time is second, it should be per second. If this is in minutes, this should be per minute. If this is in hours, this should be per hour. This is in years, this should be per year. Because you know the exponential function has no units, so the units of lambda and t should get cancelled, right? Remember that simple things. Okay, so I know the current activity, that is 6.75 10 to the power 10. I need to find A naught 40 years back minus lambda we know 7.90 10 to the power minus 3 into 40 years. So you know how to solve it. Substitute in the calculator, exponential, everything. Find the A naught. You will get A naught 9.26 10 to the power 10 BQ. So that was the activity 40 years back, right? So power released by the radioactive sample is given by power released by the radioactive sample is given by activity into energy per decay. So already we found it, energy per decay, the previous part. But in this part, the energy per decay is given as the energy of the alpha particle. I already explained the reason for that. So activity 9.26, 10 to the power 10. We are finding the power of the source 40 years back. So we should use the activity 40 years back into energy per decay. That is the energy of the alpha particle. That is energy of the alpha particle. I am telling it again. Energy per decay is same as energy of the alpha particle. The reason most of the energy per decay will be taken by alpha particle. The reason mass of the alpha particle is much lower than mass of the uranium nucleus that also produced during this alpha decay. So energy per decay is energy of the alpha particle, that is 5.6 mega electron volt. So this is as a unit mega electron volt. This is we need to convert this mega electron volt into joules. So mega 10 to the power 6 into 1.6 10 to the power minus 19 joules per second. So you will get joule per second. That will be watts. 0.083 joule per second or watts. We can use this equation only for radioactive samples. Okay, the last part, question number 19, the last part, part C. Another source that was used in early pacemakers was uh, promethium 147. This emits beta particle. The energy spectrum of beta particles is shown. So you know beta particles were emitted with different kinetic energy. So they are giving a distribution curve, y-axis number of beta particles, x-axis beta particles energy in terms of kilo electron volt. Second graph below show how the range of beta particles depends on the beta particle energy for different materials. So how the range, you know the range means how much a particle can travel through a medium, that is called range. So the maximum distance a particle can travel through a medium is called range. Say for example, if I say range of an alpha particle in air is 5 centimeter, means it cannot travel more than 5 centimeter through air. So that is the meaning of range. So they are giving a graph, y-axis beta particle, range in centimeter, x-axis energy of the beta particles. Three different lines are given for different type of materials: lead, aluminium, and polyethylene. Right. It is suggested that a layer of polyethylene of thickness 0.5 centimeter would be able to absorb all the beta particles emitted from the uh, element promethium 147 source. Comment on this suggestion. Okay, so this graph, careful, the second graph we need to use. So they are saying the thickness is 0.5 centimeter and the energy released by the promethium 147 source has maximum energy of the beta particle is almost, maybe I can take it as 225, slightly less, I can take it as 225 kilo electron volt, not exactly 225 because it's somewhere slightly less than 225. You can see the graph. So the distribution graph is given like this. So where it's cutting, this is the maximum energy. Here is the 200. So this is 250 here. So this is not exactly center between 200 and 225. So that is the x-axis is energy in kilo electron volt. In kilo electron volt for the beta particles. So that is somewhere closer to 225, I can say. So the number of particles released is 0. But anyway, how many particles are released? 0, doesn't matter. So that will be the possible maximum energy of the beta particle, but no particles are released that time. I know that. So there are particles released slightly less than 225. So we can find it from the graph. Maybe no numerical values are given, but I will take just maximum energy of the beta particle is 225. No particles released, but slightly less than 225 I can take, but I'll take it as 225. Okay, so the idea here is use the second graph. So there, on the y-axis, the lines are marked on the y-axis like this. So that is a bit confusing. So three graphs are drawn like this, and there are lines are marked like this. The scale like this. Then there are lines are marked like this. Second set. Then there are lines are marked like this. Okay, so how to take the value? So you can see here this x-axis starting from 100. Then here ending 1000. There are between that there are 1, 2, 3, 4, 5, 6, 7, 8 lines are there. So the next one is 200, 300, 400, 500. That's the way we should take the x-axis values. Okay, each division indicates 100. So 100, 200, 300, 400 and so on. So on the y-axis, this value is given as there are 10 lines. 1, 2, 3, 4, 5, yeah, 1, 2, yeah, 0.01. This is 0.01 given. Then here is given 0.1. Okay, so if it is 0.01, so what could be the value of next one? So this is 0.1 means divide equally. So this is 0.01. So next one is 0.02, 0.03, 0.04, 0.05. Count it, you will get 0.1. Try. The next line of 0.01, take it as 0.02, 0.03, and so on. It will end up with 0.1. Then here it's starting with 1. So this is ending at 0.1. So this will be 0.2, 0.3, 0.4, 0.5, 0.6, 0.9, finally end up with 1. Then the last one, there are lines are there ending up at 10. So you can take here 1 means the next one 2, 3, 4, 5, 6, 7, 8, 9, 10. You can check it, it will work, right? Okay, so now how to find whether it will completely block. For example, a sheet of 0.5 centimeter thickness of polyethylene, will it completely block the beta particle emitted by promethium 147? So the maximum energy, if I take 225, or something like 215 or 220, something like that, you can take it. If I take that's the maximum energy of the beta particle, use this graph somewhere here. How much is it? So first line is 100, this is 200, this is 300. So somewhere here take a value, and the polyether line is this graph. So for that value, you can take this is 200, second line. So the next line is 300. So 225, if I take somewhere here, take a value here and find the thickness, that will be less than, much less than 0.5 centimeter. So certainly it will block the all alpha, all the beta particles. Okay, from the graph you can find it. So you can name this graph 1 when you're answering. You can name this graph 2. Again, I'm telling it. So maximum energy I can take around 225, 220, something like that. So maximum energy from the second graph, something like this is 100, 200, next mark is 300. So 220 means somewhere here closer. Find at the point where polyethylene, what's the thickness, you will get it much smaller than 0.5 centimeter. So that will block, much smaller than 0.5 centimeter is sufficient to block the beta particle of energy 220. That is the maximum energy, means it can completely block all the beta particles emitted by promotium 147. Okay, so that's the end of discussion of this uh, May-June 2021 Unit 5 IAL paper. So if possible I have time, I'll discuss the next paper next time.